LAN technologies and protocols. A network topology describes the layout of the network and how it interconnects with other devices and network segments. Remember, we use topologies too in the green field for the selection for our data center. So read the topology in this case, how does the network look around us? The two most commonly used LAN technologies by far are Ethernet or Wi-Fi. Ethernet where you plug a cable into your computer, and well, Wi-Fi where you use Wi-Fi. And on the data link or the physical layer where we actually plug the cables in, we've used a wide range of LAN topologies. Some of them are still in use and some of them are legacy. They include ring, bus, mesh, and star topologies. And just as a layout, we've also used different protocols on the higher layers to ensure our communication. NetBEUI, IPX, SPX, AppleTalk. They used to be really common, but are not really used anymore. At this time, TCP/IP is really what we use on all our systems. Since we just covered cables, you already know that we most commonly used fiber optics between our switches, our servers, in our data centers, and then for our IP backbones. We very rarely use fiber all the way out to our workstations. And the type of connections we use today is Ethernet, but remember, Ethernet is not just copper twisted pairs, it's also coax cables and fiber cables, and it's baseband. And just like so many other things that we use today, Ethernet wasn't built for what we use it for, so all the functionality we need and a lot of the security has been bolted on. And then we're going to look a little bit at wireless, how we use Wi-Fi, devices it's built into, and how, if configured right, we can allow our employees to move seamlessly and unrestricted from one area to another without their connection dropping and them noticing they move from one access point to the next. We also touched briefly on CSMA, Carrier Sense Multiple Access, and the two different types we use today. This is where our clients check, is the line in use? If not, they send their data. If it is in use, wait a random amount of time in milliseconds and then try to retransmit. And they keep doing that until they're allowed to send their data. In CSMA-CD, or collision detection, this is what we use for systems that can both send and receive at the same time, like Ethernet. This is where, when we moved away from hubs and we started using switches, each switch port is its own collision domain, and since there's only one host on each collision domain, there are no collisions. But how it was used and how it was originally designed was exactly like above. They see if the line is idle. If it is, they send. If it's not, they wait. But if two clients see the line is idle and both of them send at the same time, we have a collision. So we added on collision detection. Just like with plain CSMA, they listen, is it idle? Then they send. They wait with a random timer on milliseconds. But now, while they're transmitting, they also monitor the network. If someone else is sending as well, meaning more input is received than sent, they know another workstation is also transmitting. We will send a jam signal telling the other workstation to stop sending. Again, wait for a random amount of milliseconds and then start retransmitting. This did work, but again, if you have 10, 20, 30 computers on the same hub, it's very easy for it to get congested. And at the time when hubs were really common in the early 2000s, switches were very expensive. At some point the prices started dropping rapidly. Switches were almost at the same price as a hub. So naturally, since it's a better product, most people switch to, well, switches. We also talked about CSMA-CA, or collision avoidance. This is what we would use on systems like our wireless, where a system can either send or receive. Just as with other CSMA, they check if the line is idle. If it is, they send. If it's not, they wait a random amount of milliseconds and then they send. This is different though than collision detection. On an Ethernet network, the clients would normally be aware of the other clients. On wireless, they're not. All they see is themselves and the wireless access point. So with collision avoidance, if there's a lot of congestion, a client can send an RTS or a request to send, and if the host, in this case the wireless access point, replies with a clear to send, similar to a token, the client will transmit. If they don't get the token back, they hold off. And the request to send and the clear to send is designed to somewhat alleviate the fact that we don't know if anyone else is connected to that access point. It's not super efficient, but that is how wireless access points work for now. Only one node is clear to send at a time, and who it is determined by the access point. Let's look at a few of the legacy LAN systems, and then let's cover the topologies that we use now and the ones we've used before. ArcNet, or Attached Resource Computer Network, used network tokens for traffic, which meant there was no collisions. It used a star topology and had speeds up to 2.5 megabits per second. Token ring networks use network tokens for guiding its traffic, and because of that, again, no collisions. It used a ring topology and it was up to 16 megabits per second. FDDI, or Fiber Distributed Data Interface, used token bus for traffic, again, no collisions. They used a ring topology, and FDDI was based on fiber cables. Because of that, it was not susceptible to EMI. Also at the time, just like now, fiber was much faster than copper was. They got 100 megabits per second. In the bus topology, every single node along the path is connected to the same line. Each node inspects the traffic and passes it along. You can think of it kind of like a chain of Christmas lights. And with the Christmas lights, if the cable is broken at any point, it doesn't work. If we look at the topology over here on the right for the bus topology, let's say the third workstation from the left has a faulty network card, it breaks the connection. That means node 1 and 2 can communicate with each other, and 4, 5, and 6 can communicate with each other, but nothing passes in any direction from 3, and 3 can't communicate with anyone. And the connection break can be a bad cable, but it can also be a faulty network card. This is a legacy connection. We do not use bus topologies anymore. In the tree topology, the base of the tree controls the traffic, the mainframe is the roots of the tree, and everything else is attached to that. But just like the bus topology, if a single node fails, everything beyond that point can't connect to everything on the other side. Also legacy, also not used. Ring topologies are also legacy topologies. They're not really used anymore because they're not efficient. They do, however, have advantages over a bus topology or a tree topology. Let's pretend the node at the top breaks. The node to the left of that and the one to the right can still connect to each other because they have a path the other way around. But legacy, not used. What we do use today is the star topology. All nodes are connected to a central device. This is what we use for our Ethernet. The center of the star is our switch. If again the workstation at the top dies, the NIC fails, the cable dies, the cable is cut, whatever happens, it only affects that one workstation. And if we use a switch, we don't need token passing, we don't need collision detection, anything like that, because every single node is segmented off on its own collision domain. Hubs also use the star topology, but I really hope we don't have any of those left out there. But I also have to be realistic, we probably do. If you have those in your network, you should really look at getting rid of them. Not only are they horribly inefficient in how they handle traffic, but they're also very unsecure. And switches are pretty inexpensive now. So if you see them and you have them in your network, buy a switch and replace them. In mesh topologies, we talk about either partial mesh or full mesh. In a partial mesh topology, some of the nodes are directly connected to each other. One node might be connected to everything and the rest only to a few other nodes. Whereas in a full mesh topology, every single node is connected to every other single node. Full mesh is obviously more redundant, but it also requires a lot more networking cables and it requires more networking cards. In the topologies we have over here on the right, each node would need 5 networking cards and 5 networking cables. And depending on what we're trying to achieve, we could either use partial or full mesh. It is still used, mostly for high availability environments or places where we use load balancing. But in those cases, each of the server will have a connection to a switch, which is used for the actual data, and then the partial or full mesh is used to communicate with the other servers in that server cluster, either for keep alives or just for load balancing. We use keep alives if we have a server pair or a couple of servers that are redundant. If we take an example of we have a primary and a secondary server, only one of them is used for actively processing data at a time, that would be the primary or the master. The secondary or the slave would then, at a predetermined interval, every second, every 2 seconds, 3 seconds, something like that, send a keep alive saying, "Hey, are you alive? Hey, are you alive? Hey, are you alive?" If the primary server replies back, the secondary server does nothing other than send another keep alive. If the primary server does not respond back, and it misses normally 3 keep alives, the secondary server thinks it's dead, and it takes over and becomes the primary server. So that's really where we'd use partial or full mesh topologies.